This video lesson is for Chapter 5, Part 2, Magnetism and Electromagnetism. Phenomena that deal with magnetism can be found in a lot of places, but one important phenomenon is the Earth's magnetic field protecting all living things on Earth from radiation from space or from our Sun. 2.1 Magnets. Magnetism describes all the phenomena caused by magnets. And a magnet is an object that can attract other ferromagnetic substances, which are iron, cobalt, or nickel. It was given this name because it is thought to have been discovered around 600 BCE in the region of Magnesia by the Greeks. Magnets strongly attract iron, nickel, and cobalt and other rare earth metals. These substances are ferromagnetic, meaning that they are not magnets, but they can become magnetized if they're brought near another magnet. Compasses are made with magnets also. The needle at their center is always magnetized and will point towards the Earth's geographic north. All other substances are non-magnetic. So, we have magnets, which can attract or repel other magnets. We have ferromagnetic substances that will be always attracted to other magnets, and the rest is non-magnetic. For example, plastic, copper, aluminum are non-magnetic substances. The mineral called magnetite, that's magnetite, is a natural rock that can be found in nature, which is already magnetic. The magnets you'll find in stores or in labs are usually made of mainly iron and have to be magnetized or remagnetized over the years. All magnets have forces of attraction or repulsion. All magnets have a north magnetic pole and a south magnetic pole. The north pole is represented by a capital N and the south pole a capital S. Opposite magnetic poles will attract each other. So if a north faces the south of another magnet, they attract each other. That's an attractive force. And like magnetic poles will repel each other. So if a north faces the north of another magnet, they repel each other. Or if a south faces the south of another magnet, they also repel each other. So it would go like this. If we have north, south, in the next magnet, south and north, these magnets will repel each other because the lines of force of the magnetic field will not be pointing toward each other. Those lines will be pointing away from each other. So that's repulsion. If we have a north pole facing another north pole, and this on the right is south, we will get the same shape of magnetic field lines. They would never touch each other, but they would be going in the other direction. And that's also a repulsive force. But if we have a south pole facing a north pole, or a north facing a south, then the lines of the field would be going from one pole to the other, creating a force of attraction between the two magnets. So the north pole of a magnet is the end that naturally seeks the Earth's south magnetic pole, which is near the geographic north pole. The reason why there's a force of attraction or repulsion in magnets is the fact that they have magnetic fields. The magnetic field is the area of space in which the magnetic force of a magnet can act on another magnet. We are aware that if we bring two magnets very close to each other, we can actually feel this force of attraction or repulsion. But the farther away we put the magnets from each other, the smaller this force becomes. Now, the magnetic field of a bar magnet looks like this. We will start north and form about half a circle that goes south. So this one is going south. Then again from the north, underneath, but also going south. We can trace a couple other lines that are incomplete, but that always leave from the north. If we had more space on this page, we could continue these lines under and on top. Now we have to imagine here you have an infinite number of lines of the magnetic field, but we are only drawing the main ones. Same thing on the other side. we would have those large lines coming towards the South Pole. So the lines always go toward the South Pole and always away from the North Pole. Now in geography, we were always told that the Earth's North Pole is situated on top. So we place it on top relative to our position on Earth, and the South geographic pole is under relative to our position. But we have to understand that these points mark the axis of rotation of the Earth. When using a compass, the compass points towards that north geographic pole, but not exactly at that point, because the compass is always pointing at the south magnetic pole, which is placed near the north geographic pole. That means that in the southern hemisphere, what we call the south geographic pole is actually the north magnetic pole for the Earth. When you use a compass, you have to keep in mind that your needle is a magnet, in which your red or dark tip is a north magnetic pole, so the other tip of the compass is a south magnetic pole. So it's a magnet. So if I approach the compass near another magnet, the north magnetic pole of my compass will always align itself towards the south magnetic pole of that other magnet. And when we use a compass regularly on Earth, your north magnetic pole of the compass, so the red end, always points towards the south magnetic pole of the Earth, which happens to be nearby the geographic North Pole. This slide is just to reinforce the idea of the compass always pointing towards a south magnetic pole. So here we can see the red line on the diagram. I'll make this one a bit more obvious. That red line marks the axis of rotation. That's where we have our north geographic pole and south geographic pole, but the poles of the magnetic field of the Earth are not exactly on those spots. So that's our south for on top for us, and the north magnetic pole is under for us. So if we place a compass anywhere around on the planet, it's going to align like that. We're going to have the north pole of that compass pointing in the direction of the south magnetic pole, and we're going to have the south magnetic pole of your compass pointing in the direction of the north magnetic pole of the Earth. Let's look at what happens if we place a compass around the bar magnet. So we'll start with the one near the south magnetic pole of the magnet. We said that a compass always points towards the south magnetic pole. So this one points towards south. That means it's going to have to be pointing away from a north magnetic pole. So the one near the North Pole points away from it. It's being repelled by that pole. To trace the other ones, you have to remember what the lines of the bar magnet looked like for its magnetic field. So they would leave out straight like this from both ends, but then they curve around. So we're going to have a curve like this everywhere. It forms some kind of circle around the bar magnet, always from north to south. So your compass is always going to follow those lines. So on top, and your compass is following the lines going towards the South Pole. Under, same thing, following the lines going towards the South Pole. On the right side, always following the lines, same thing on top. And on the left side, always leaving the North Pole, going towards the South Pole. So the compass around the bar magnet does not necessarily point directly towards the South Pole, but it follows the lines of the magnetic field traveling towards that South Pole.